Good evening, and welcome to Science Never Stops with the U.S. Space and Rocket Center. My name is David Weigel, and I am the Intuitive Planetarium Director, and I'm very, very excited to welcome you to what is our last live stream in the Science Never Stops series for at least a little bit of time. And let's see, I'm going to fix my imagery. It's This actually has not been imaged yet, but we'll talk about that in a moment. Let's go back to one day from now. There we go. We'll continue our orbit, and that'll look pretty. All right, so that totally messed up my introduction, but starting over. This is our final last stream in the Science Never Stops series, and you may be thinking, well, David, that doesn't make any sense. Science never stops, so why are you stopping your live streams? And the reason is we are very excited to reopen the Intuitive Planetarium, and we'll be reopening for Friday evening events only at this point, and we'll be doing so starting next week. So next Friday at 7 p.m., instead of joining me online virtually, you can join me in the Intuitive Planetarium at the U.S. Space and Rocket Center in Huntsville, Alabama. I understand some of you live around the world. You'll have to figure out how to get here, I guess. That could be very exciting. Or possibly illegal, so don't do that if it's illegal. But we will be hosting a special director's cut of Our Place in Space, which is maybe a good bit longer version of this show with that's actually really not this show at all, but it kind of is. It will take a look at our place in space, quite literally. We're going to take a look at the Earth as it resides within the solar system, sort of hit the major worlds of the solar system, and then zoom you far away to get a sense of perspective. In this presentation, we're going to do sort of a look at the Earth very briefly, but then take a look at sort of grander scale of things and give you a longer sense of perspective and try to make you feel very, very small. That's my goal tonight, I guess. So that should be pretty exciting. So feel free to let me know where you're watching from, and I will let you know if you are able to come, I guess. And let's get this rolling. So I want to point out that the software we're using tonight is called OpenSpace. It's from the OpenSpace project, and it is something that we have used in previous live streams, including last week, when we explored the moon in great detail. And so I definitely recommend this for you to download on your own, because it is free and open source, and you can go to openspaceproject.com and download it there. You do need at least a reasonably decent computer to run it, but I have faith in you that hopefully you or somebody you know has one. And what's really neat about OpenSpace is its ability to view planetary data sets and just large data sets in general, and do so in context. So right now we're taking a look at the Earth. We're orbiting very nicely. I'm going to switch that up. I'm going to click and drag around using my mouse. I have friction turned on right now, or off rather. So when I click in a direction, it continues me moving until I tell it not to do that anymore. But what you can see in here, let's actually, I'm gonna sort of pause our view here, and we're going to very, very slowly zoom in. And I want to bring us just a little bit back in time. Let's go back a few hours so we can get a little bit more full view of the United States. This is imagery from a couple days ago now, and you can take a look. This is Tropical Storm Cristobal, which is heading sort of into the Gulf. And this is really neat, cloud layer imagery, and it's near real time. So this is a true color sort of corrected reflectance from the NASA VIIRS instrument. So basically this is looking at visible and infrared light that reflects off of the Earth in various different wavelengths, and through some data processing, they're able to take different bands to mimic what our eyes see of both the Earth, the ocean, like the land on the Earth, the ocean, the atmosphere, and give us a really nice sense of what weather looks like above the Earth, what the Earth would look like if we were sitting, say 6,000 kilometers away from the surface here. So you can pay attention to this up in the top left hand of the screen if you're on a bigger screen and can read this, and can get a sense of sort of where we're going. So the focus in here, that's the center of the Earth, which is about 6,000 kilometers in radius there. And you can see from about the surface, we're about 5,000 kilometers away at this point. So a couple days ago, you could see that Cristobal was having sort of, it was kind of dying down a little bit, and it has apparently, I'm not a weather person, but it has reinvigorated and is sort of moving its way up. So if we were to advance time one day, pop around here, you can see that it is slowly gaining traction again and sort of moving forward. So it was sort of fizzling out a little bit a day ago, and now is gaining steam once more. If we were to change this back to like the 1st of June and go back a couple times, there we go. Wait for my internet to catch up, which has been very, very poor today, unfortunately. So my apologies if that affects us. But you can get a sense of what that looks like. And it's quite nice resolution, as you can see in here, and just one of the neat things. We're losing a little bit of the opacity because as you zoom in further, the default in OpenSpace around the Earth is to have sort of a combined data set of this real-time imagery and then a very, very, very high resolution imagery of the Earth itself. So once you get too close, or enjoyably close, then we can start to perhaps make out some really, really beautiful things. Okay, so I want to zoom you in just a little bit to bring you to the Huntsville area, just to give you an idea of where you need to come next Friday at 7 p.m. Oh, cool, and now I can see all of your comments. Like I said, my internet's struggling royally. So hello from Wisconsin, Memphis, Indiana, Atlanta, Florida, all over the place. Hello to Ashley, Carrie, Cindy, Barbara, Stacy, Joyce, and Benna. Very cool. And OpenSpace, hello to you too. Okay, stop paying attention where we're going. Let's see, I think I hit my spot pretty nicely. Yep, okay, cool. It's hard to monitor comments and give a planetarium show. A lot easier when you just talk to me. So, zooming in a bit, this is the Tennessee River in here, and you can see sort of Huntsville proper, and we're close to Huntsville proper, but not quite there. Zooming in a little bit more, slowing down our approach in here. You can see a nice golf course right there, and as we zoom in a bit closer, we have our lovely campus, the U.S. Space and Rocket Center, which is situated right in here, and you can see an enormous shadow from a very large Saturn V rocket. Also our Pathfinder shuttle in here, and various other rockets in Rocket Park. Saturn I right in here. And if you are coming to the museum, now that we've reopened, we are temporarily parking over here for an entryway through the Davidson Center, which actually brings you right by the Saturn V. So park over here, and you'll have all sorts of awesome times. And the planetarium, of course, is situated right in here. So you can see this is pretty incredible resolution. Certainly you could get something like this with Google Maps or other things, but you have it nicely wrapped on a world, and you can explore more than just the Earth, and that's what we're going to do right now. So we're going to gently pull away here from the Earth, and you'll see that Veer's cloud imagery pop back in a moment. While we're zooming away, I do want to point out that if you're doing this for yourself, again, you can see some stats up here, but you can pop open this scene menu, and it tells you what you're looking at, but it also tells you what different types of layers that you could choose from, and you can play around with this some on your own time. I do want to slow down our approach here, or our departure here just for a bit, so that we can take a look at this line in here. This is the International Space Station, which is currently orbiting about 250 miles above the Earth's surface. And in the grand scheme of things, that's very, 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 very close. And we are super excited to have a successful launch from American soil just about a week ago, or something like that. And first one since, I believe, 2011. And this is very, very exciting because now we do have a means to bring astronauts back to the International Space Station, and excitingly, beyond that, once we try to send astronauts to the moon and perhaps Mars in the near future. Near future meaning I don't know what that means. As we head away from the Earth, you'll realize that I'm going to turn on labels, or on orbits here. You can see the moon's orbit right in here, and this really is not very far in the grand scheme of things. You can see that our distance away is about 3 million kilometers, and as we start to zoom farther and farther away, you can see some very bright patches over here and over here, sort of where my face is when the mouse disappears. So that is looking into the plane of the Milky Way. We'll talk more about that in a minute. But over here, these are looking at the different orbits of moons of Jupiter and Saturn. So Jupiter right here, Saturn right here. And you can actually see Pluto just barely right out here as well. Glance at the sun, and so planets from inside out: Mercury, Venus, Earth, where we just left, Mars, Jupiter, Saturn, Uranus, which is somewhere over here, Neptune, there we go, and like I said, Pluto right in there. Except that Pluto's a dwarf planet. That's a conversation for another time, maybe next week. So as we're sort of cruising away, let me slow down our departure once more. And I think it's very useful. We're going to sort of minimize that menu. I think it's very useful for us to take a look at constellations. Because, nope, these constellations, there we go. Because as we're zooming away, constellations are something that we're all familiar with. Maybe you don't know where they are exactly, but you know at least that they exist. Oh shoot, and I've been missing all your comments because it wasn't scrolling down. My apologies. I'm glad to see that you like the launch. Can we see the asteroid that's supposed to do a flyby tomorrow at 3 million miles away? Ooh, great question. And if I had prepared for that, yes, but I didn't, so sorry. So no. Anyway, constellations are something that we're at least familiar with their existence, and that they are very, very uniform for us, right? So we should at least be able to find a few stars that are recognizable in the sky, I hope. And you might recognize things like, for example, the Big Dipper, which is actually an asterism, not a constellation. You might recognize things like Polaris, the North Star, which is part of the Little Dipper, or Ursa Minor. You may recognize things like Orion, or Orion's Belt, which is the sort of recognizable part of the constellation. Orion's Belt itself is an asterism. But these things are very, very recognizable to us in the night sky, and they are constant. So even though they do change seasonally, after you get back to the same season, they're there again in the same place in the sky. And as long as you're at the same latitude on the Earth, you're going to see the same sky. And if you saw the sky or if the Earth was a point and you could look at 360-degree view of the sky, you would see all of these constellations, except in the direction of the sun, which would be blinding you. And that wouldn't work anyway. But the point is that these things are these two-dimensional pictures from our perspective, but they're incredibly arbitrary, and that's something that's very easy for us to forget, because as we start to zoom away and we start to recognize the three-dimensionality of space, this soon becomes very different and a little bit ominous, right? The closest star to us, Proxima Centauri, is about 4.2 light years away. We talked about that in the exoplanet show we did not too long ago. And a light year is a tremendous distance, right? It's the distance that light can travel in 1 year. And light travels at 186,000 miles per second, or 300,000 kilometers per hour. right, or per second. So this is an incredibly large distance, incredibly quickly. And yet it takes light from that nearest star 4.2 years to reach us. So space is incredibly vast. And when you think about traveling from state to state, if you live in the United States, potentially that is a longer distance traveled than traveling to, say, the International Space Station. Gravity, of course, is not working against you in the same way, so it's not an apples-to-apples comparison, but the distance is not very far away. But then when we get to other planets, you're talking a significant amount of time, right? When we're trying to send a signal to Mars to talk to different spacecraft, a rover, for example, you might be able to get there in as few as 3 to 5 minutes, perhaps. It might be as slow as 24 minutes for a one-way signal. And so space is very big. That's just Mars. When we get farther and farther away, you get these incredible distances that need to be surpassed in order to navigate places, and that's why we're sort of stuck, so to speak. So I want to turn us around. You can see where all of these stars reside, right, that we can see in the night sky, and maybe we see perhaps 5,000 to 6,000 stars at any one point in the night sky, and all of the stars that we can see from the Earth, maybe that's 9,000 to 10,000 stars or so, and they're all in very close proximity, compared to the grand scheme of things. Quick question from Dan Moffat. Thanks for watching. Why is the Big Dipper not a constellation? It's a great question. Constellations, compared to asterisms, are a little bit more historical in nature. They're a little bit more complex picture in the night sky, a little bit more involved. They typically have some mythological associated stories with them, although not necessarily, especially for the southern hemisphere constellations. And asterisms are sort of a more easily recognizable picture in the night sky. You're looking at things like the Big Dipper, things like Orion's Belt, the Summer Triangle, which you should be able to see in the later evening at this time of year. So these are simpler pictures in the night sky, more easily recognizable, and things that hopefully you can see a little bit more easily. I don't know. Conversation is escaping me at this point. So the point is a little bit less defined, a little bit less official. You could make your own asterism, and that would be super cool. And if you got a lot of people on board and they started talking about it, maybe I would too, and that would be fun. Okay, so let's. We're getting ahead of ourselves, and I need to turn off constellations for right now. You get the point, and we'll bring that away. Okay, we're going to zoom out of it. Question from Frank. How long have you worked with NASA? Technically, I work at the Space and Rocket Center, which is the official visitor center for NASA Marshall here in Huntsville, and have worked here for a little bit over a year, February 27th of 2019. So, pretty exciting. Okay, and hello to Bill and Joyce as well. Okay, so we're taking a look at our galaxy, the Milky Way, and this is a relatively new addition to OpenSpace, which I think is extremely beautiful. This right in here is a volumetric rendering, and everything that you've seen so far is all real data and real imagery. This is real data, but it isn't real imagery in the same way, because since these distances, like I just talked about, are so big, so far away, you might even say astronomical, we do have limitations of where we can take things. So you can't send a spacecraft outside of our galaxy. We've barely sent spacecraft outside of our solar system, just barely. The two Voyager spacecraft, Pioneer 10 and 11, New Horizons is at least on its way. We're really only talking to Voyager 1 and 2. So these things are all on escape velocities, but nothing else is. So you have to get going incredibly fast and travel for quite some time to even get close. So what you're seeing here is a volumetric model that, in OpenSpace, you can correct me if I'm wrong, but I believe this is based on the Hipparcos catalog, perhaps with some Gaia data built in, but not the whole catalog, certainly. These are different stellar catalogs that help map the 3D nature of our galaxy. But Hipparcos is only about 100,000 stars. Gaia is much, much, much better. It's about 2 billion stars, a huge, huge improvement. But that's still not very much in the grand scheme of things, because our galaxy is home to maybe 100 to 400 billion stars. So this is a very, very small sampling. But from our place in space, within the Orion subarm, which is about 26,000 light years from the galactic center, we can see various different things in various stars in different places in our galaxy. We can see that the center is incredibly, incredibly bright. It's very bright and yellowish because it's a lot older stars are very densely clumped, compared to the spiral arms, which are a good bit bluer because they're younger stars. There's more fresh stellar formation happening in these spiral arms. And we also get a sense for what these galaxies look, or what our galaxy looks like, from imagery of other galaxies that we can see from our perspective. And OpenSpace is giving me the thumbs up, so that means I explained their volumetric model well. Cool. So again, I feel like this is a very, very detailed rendering, one of the best you can find, I think, in certainly free software, and looks really cool. Let me show you where we are. So if we bring up our, what am I looking for? Milky Way volume. Not what I'm looking for. That's okay. You can tweak all sorts of things, all sorts of parameters in OpenSpace, and that's super helpful. Let me zoom back in for just a moment. We talked about exoplanets last time, and where they were located from our perspective, but I do want to give you a sense of sort of how close all of these are too, because if we're talking in terms of 100 to 400 billion stars, there are so many exoplanets that we have found in a very, very small window of searching. Right. So when I turn on this this yellow data set, this is the Kepler field right in here, and various Kepler planetary candidates and observations. So all of these blue things, turn that back off, all of these blue things are all confirmed exoplanets. All the yellow ones are potential exoplanets, aided by the Kepler Space Telescope, which is now decommissioned, unfortunately. And you can see that it didn't look in a very large swath of space. You see these sort of cones, and that's not, it's not that it looked in the whole sky and it just saw something in one spot, but rather that it looked in this particular field of view, in this case near Cygnus the Swan, and the constellation Cygnus. And you can see how many candidates are found in these locations. So we're looking at about just over 4,000 confirmed exoplanets and maybe 5,000 to 6,000 candidates. And that's looking at very small regions. So perhaps you're looking at an exoplanet for every star, perhaps more. You might have 500 billion exoplanets just in our galaxy alone. So it's starting to give you a sense of scale here and how far away things are, I hope. Zooming out a little bit, also from our point of view, we can take a look at where various other things are. And one thing that I think is pretty neat are taking a look at pulsars. The reason that I think pulsars are very interesting, all of these things are interesting, but in particular, I find pulsars very interesting because they are stellar remnants, but they're stellar remnants that act as sort of like a stellar lighthouse. It is a neutron star, which is the result of a supernova, where the core of a star collapses on itself, and at a subatomic level, a proton and electron get too close together, and so they literally combine into a neutron, release tremendous amounts of energy, and the entire core of the star does that. So you're just left with this neutron stuff, right? Packed super, super tightly, extremely dense, about the size of Manhattan Island or something. Very small. And spinning incredibly, incredibly rapidly due to conservation of angular momentum. We're going to go through the core here, and that's going to look very cool. And so they're spinning very, very rapidly, and if they have a strong magnetic field associated before their demise, then they can beam out huge streams of charged particles and electromagnetic radiation into space. And if we're within that beam, as it sort of whips around again and again and again, we can see that signal. And they pulse, and they do so with incredibly high precision timing. So these are like the most prime clocks, stopwatches in the universe. So they're very, very useful to us, and they help us to very fine-tune where things are located in our galaxy, because we're able to, based on their extreme ability for precision of timekeeping, we're able to get a sense of distances very nicely at these scales. So you can see lots of pulsars, and they spin very rapidly. For example, the Crab pulsar and the Crab nebula, which you should look up. It looks amazing. Maybe we can link to a picture of that. Aaron, if you could do that, please. It's amazing, but the Crab pulsar spins 30 times every second. So that gives you a sense of how fast these things can spin. So we could talk about various things in here for a while, but I'm going to zoom out a little bit further because we have bigger scales to get to. So let's sort of refocus our efforts over here. There we go. And zoom away a bit. And as we start to zoom away and that fades out, you'll start to notice various dots come into view. And let's bring up some different things in here. So I'm going to bring up the local group. And the local group, all of these green dots in the foreground, there's about 100 or so, and 60 to 100 or so. And the local group of galaxies is what the Milky Way is a part of. It's the closest galaxies to us in our localized region of space. Pretty self-explanatory. And they are, these are our nearest neighbors. If we ever had any hope of traveling intergalactically, which we don't at this point, this would be where we go. So some you probably have heard of, like Andromeda, which is the largest. The Milky Way is the second largest. And you have things like Triangulum Galaxy as well. And then plenty of smaller ones too. I should point out too that the Milky Way, I told you, has about 100 to 400 billion stars. In terms of size, it's about 100 to 150,000 light years in diameter. And again, we're about 26,000 light years from the galactic center. Zooming away, we're going to take a look. We've got a few different galactic surveys turned on. And the different colors here represent a few different things. So let's see. When we look at orange, you can see that orange are very, very tightly clumped together. And these are going to be the most dense regions. So these are galaxy clusters and filaments. They give you a sense of this very tight-knit structure of the galaxy in some places, or excuse me, of the universe, of these galaxies tightly knit. The sort of bluish aqua is going to be these sort of intermediate density regions. You can see fewer of those. And then the green galaxies are ones that are sort of in empty areas. And so it's a neat visual. At first, the first time I saw this, it sort of hurt my eyes a little bit. And my mind didn't want to comprehend. And then I sort of thought about it, and it was a very useful visual so that you can get a sense of structure very nicely. So again, when you're looking at orange, that's very tightly clumped things, but these green things are much farther away. So right in here, we're looking largely at telegalaxies. And this is a compendium of about 30,000 galaxies or so. Which sounds like a lot, but isn't so many. And it's actually truncated in a nice sort of cubic fashion so that you can get a sense of structure, but at the same time you don't get any sort of conflicting data when you get farther away and you start to obscure galaxies that are a little bit too dim to see, and that throws off your view of structure. So this gives you a neat sense of that. But what I also think is very cool, if we sort of switch those out, I didn't do that very well. Let's try this again. Let me scale this up. Well, too much. Okay, cool. So you can find the sweet spot on your own, but in the place of where all these points are, you can also toggle two-dimensional images which sort of point in their correct orientation in space. And the image is not the image of the galaxy itself, but rather it's, if I'm correct in understanding, it's the right class of galaxy, and more or less the right color if it's red shifted or blue shifted, meaning going towards us or away from us, that sort of thing. So this is quite beautiful. And this is something that we can represent in the planetarium as well. And spoiler alert, if you come next week, you might see something awesome like this. And it's very cool on your computer screen or on your phone, but it's really, really cool on a 67-foot dome, no doubt. So with 35 million pixels to bounce at your eyes. Cool. So zooming farther away, we are going to head further out. And again, the Tully catalog there is about 30,000 galaxies or so. And that's all fine and good, but it only gets us about 1 billion light years away from the Milky Way. So that's not that much, really. And you can see this sort of cubic shape, but the further and further we go away, we can bring up the Sloan Digital Sky Survey. That popped in very abruptly. But this is a much, much, much bigger data set, and this is quite exciting to look at. There are about 1 billion objects in this data set, but they're not all galaxies, certainly. Many of them are stars that are closer to us, but this is a look at about 35% of the sky, and you can see these very characteristic sort of voids, cone-shaped voids, or rather cone-shaped not voids in here. And this is maybe a curious thing to think about. Why is this what space is shaped like? And it's not a matter of what space is shaped like, but rather what our viewing perspective is. So when you look at our galaxy, the Milky Way, and I failed to do this, and that's a huge knock on my presentation, but our galaxy is very, very, very flat. It looks sort of like a disc shape, maybe a fried egg or a pancake. And if you turn it on edge, very, very, very thin. So where it's 100,000 light years across, you're only looking at about 1,500 to 3,000 light years thick, and about maybe 10,000 light years thick in the galactic center with that sort of galactic bulge of all those older stars. So when you look edge on into that disk, which is situated in this direction, it's a lot harder to see things because you have a much higher concentration of gas and dust and stars and stuff. So we don't concentrate our efforts in that area often when we're looking for things that are far away, because you'd be disappointed in your data, or you have to try very hard, one or the other. So bummer, I guess. But this is all very, very pretty. And again, this is, you can see this the same sort of idea of so this sort of filamentary structure in here. And that gives you a nice sense of sort of what this web-like structure looks like, and the same sort of convention of coloring, where orange is going to be more clustered things, aqua sort of intermediate, and green is sort of farther away. But it's a little bit hard to tell when all this is here. You can tweak all of this data on your own to fit your monitor at your resolution and size to give you as sharp a view as possible and as easy to see as possible. So what looks really good for me right here, it's hard to tell if that looks incredible on Facebook Live or just very, very cool. So let's zoom farther away. And as we zoom farther away, you can start to see, wow, things are very, very far away. And I guess before I even go that far, what I should point out too is that this this orange data does not correspond to the same convention in here. These are quasars, and quasars are the most distant the most distant objects that we can see. Quasars are so named because they're known as quasi-stellar objects when they were first found. And the reason for the name is that it was this really, really bright source in the sky that clearly was not from our own galaxy, but it was so bright that it was thought it would have to be. These were these things that were so bright, yet so far away when we were able to start to gauge distances. And so this was a very peculiar thing as to what is this. And it was determined that these are very, very active black holes in the earliest era of the universe, right? Because as we look farther away in space, we're actually looking back in time. Because since these distances are so tremendous, and I already told you that light travels very fast, but it doesn't travel instantaneously. So when we look further and further away, we're looking very much into the past because light literally has not had enough time to reach our eyes in some cases. And in these cases, light has reached our eyes, but it's taken maybe 13 billion years to reach us. Let that sink in for a minute. So these furthest quasars are perhaps 13 billion years old in terms of the light that we're seeing, 13 billion light years away as a result. And they are from a universe, we're seeing light from a universe that was very violent. You had this supermassive black hole, the center of its galaxy, that was consuming all sorts of material, and as a result, spewing out all sorts of radiation before that material quite fell in. And we see the light from these, which is the equivalent of perhaps 20 trillion suns, or 1,000 Milky Way galaxies. So these are tremendously bright things, just very far away, and that's cool to say the least, or I guess rather hot and violent. So if we were to see the light from these things right now, as it is today, we would see a very different place, and perhaps one that is even similar to our own galaxy. Now we have just passed this sort of cosmic bubble, and that might be further confusion. And what we see in here is just sort of some yellowish red and some blue. And this right in here is the cosmic microwave background. The cosmic microwave background is a difficult concept to understand, perhaps, because it's often modeled as this sphere, and it's the farthest away thing that we can see. And the reason this is misleading is because this is sort of the shape of the observable universe. This is as far away, the furthest thing back in time that we can see, and that gives us a distance of, basically moments after the Big Bang. This is 13.8 billion years ago, something like that, to our best observations. And what we're looking at is quite literally the sort of thermal fingerprint of that experience that was sort of an infrared, kind of hot, a little bit cooler than the sun, just sort of background radiation at that time, but due to extensive amount of time and expansion of the universe as a whole, the wavelengths have expanded with that fabric of space and time, and now it's a very cool 3 Kelvin, so about 3 degrees above absolute zero, as cold as you can possibly get. So it's very cold, and it's very minimal fluctuation. And in fact, the difference in this visual of the sort of blues and the reds is extremely minimal. You're only looking at a difference of about 1/100,000th of a degree in temperature. So this is, again, that sort of background radiation from the Big Bang itself. But it is something that's persistent throughout space, 3-dimensionally. So it's not that it's this sphere around us, but we view it this way because this is sort of it projected out in space and gives us this nice bounding sphere. And beyond this, we don't know anything. There literally has not been enough time for light to reach our eyes this far away. So is there a universe past this? Yes. What does it look like? We have no idea. Will we ever know? We will not. Bummer, right? But it gives you a sense of perspective a little bit, and it looks like we're right at the center. And it's not so much that we're at the center of the universe here, but we are a bit at the center of our own universe, our observable universe, because from our perspective, everything moves away, in all directions away from us. So you are the center of your observable universe, but not of the universe. You can think about that for a little while when you're trying to go to sleep tonight or something like that. So wow, I guess. As we zoom in, we will quickly trundle back through tremendous distances away, billions of light years, quite literally, and go from a very, very early universe, a very violent early universe, a very bright early universe, into a much more calm and spread out and peaceful and perhaps boring universe that we inhabit at this present day. And as we cruise in a little bit further, let's bring, wrong thing, there we go. As we cruise in a little bit further, we'll get to our own galaxy, the Milky Way, and I'll give you what I should have given you before, wrong way, which is a neat view at this sort of three-dimensional structure. There we go, forgot how to drive. Let's see. There we go, spin that a little bit quickly, but we'll bring it kind of on edge. There we go, right about in there. You can see very thin, very nice. And we'll zoom into that. And head our way home. But despite being very, very, very far in all directions, the universe around us, despite it being very, very, very far and very vast, and giving you this feeling of perhaps near infinite smallness. That's a reasonable feeling, perhaps. But at the same time, it's important to realize, to recognize that the Earth we live in is a very, very special place. And though we've found other worlds, and we've found plenty of stars, we found these worlds around them, we haven't found another Earth. We haven't found anything quite like the Earth. We haven't found life anywhere else. And we certainly haven't found anyone like you. And so this is a very good thing to think about, with all sorts of things that are going on both now and whenever things are happening, because you are very important, and you are an integral piece of the Earth, of the solar system, the Milky Way, the universe, and the universe would be a different place if we did not have you and everyone else in it. So it's very, very important for us to recognize this, that we are all very unique and very important and have great significance. And so I hope that you take that away with you tonight, in addition to your feeling of being very, very small in the grand scheme of things, because you sort of are. But that's okay. You're important too. So as we head back to the Earth, wow, what a trip. We went from the Earth to much farther beyond and then back, and it was super cool. So go check out OpenSpace at OpenSpaceProject.com. It's a lot of fun to play with. And oh no, I dragged the wrong menu. It's really hard with lots of menus. There we go. Check it out. It's lots of fun. Very cool. There is the United States getting hit by a tropical storm. And remember that science never stops, not at the U.S. Space and Rocket Center, nor anywhere else. But this live stream does stop, at least for now, as we prepare to reopen the Intuitive Planetarium for Friday evening programming next week, June 12th, 7 p.m. We hope to see you there. Tickets will probably go on sale maybe on Monday or so, somewhere in that range. So watch our website at rocketcenter.com/Intuitive Planetarium or just rocketcenter.com. And I hope to see you next week and in person. So thank you so much. Hope you've enjoyed this series. Hopefully we'll do it again sometime. And if you have any questions, feel free to Feel free to jump on in the comments and hit me up. And in the future as well, if you have any space questions, you can reach out to me through the U.S. Space and Rocket Center Facebook page. They know where to find me. And I or somebody on my team can help you out. So thanks so much. Have a great night, and hope to see you soon. Take care.